right, so I'm going to start by telling you, some recent results involving algorithms for finding low energy states, and this is joint work by Itai Arad, Umesh, and Thomas Vidic, who's well represented in this session, as I found out. Okay, so Henry covered sort of the basic challenge in quantum systems, which is that you're dealing with an exponentially large space, and how do you sort of handle that exponentiality in some reasonable way? And and Henry basically sort of said that the way we kind of think about it is we try to wrangle the states that we're interested in into some sort of smaller place and sort of put them in some terms so that we can use them and manipulate them and work with them. So that, in fact, this large space, this exponentially large space, is sort of an overlying space, but it's not what we end up dealing with in some way. So that's sort of the overall picture of what we're sort of getting at in this thing. And so let me tell you what physically relevant states means in terms of what we're going to talk about today. It means they're low energy eigenvectors of something called a local Hamiltonian. So let me tell you what a local Hamiltonian is. So a local Hamiltonian is a linear operator on this exponentially large space. So for each particle, there's a d-dimensional space, and this is a tensor product. And we sort of think about local terms which are local operators that act locally on just a few of these particles and are trivial on the rest, to act as the identity on the rest. And a local Hamiltonian is some operator that's formed out of the sum of these local terms. H is the sum of these local terms. And we're interested in the lowest eigenvectors of these, the eigenvectors with the lowest eigenvalues of these. And this is the quantum analog of constraint satisfaction problems from classical computer science. And the correspondence is the HIs. If you chose the HIs to be diagonal in the sort of standard basis that's given, then you have a constraint satisfaction problem. And the low energy states are those states that have the least number of constraints that are violated. So from the physics point of view, one often thinks about a geometry on these local terms. So the local terms don't involve just any things. We put a geometry on the particles, whether 1D or 2D, and the locality is then reduced to acting locally. We should think of each of these black lines as one constraint HI, and this one would act on these two particles non-trivially in an AVRS, and same with one dimension. So we're going to focus, today the talk is going to focus on what's going on in one dimension. Now, classically in one dimension, everything's easy, right? But quantumly, it's not. Quantumly, it's provably hard. There are problems in here that are QMA hard as they get. Okay. So let me tell you what we do. So we give an algorithm that for 1Ds, quantum systems, so on the line, where the low end of the spectrum has a certain form. Okay, so these are supposed to be pictures of the low end of the quantum of the spectrum of the operator. And what this is saying, what we're looking at is cases where within the bottom, a constant amount of the bottom part of the spectrum, we have at most a polynomial number of states. So remember, this is an exponentially large operator. So in total, the number of eigenstates is exponential, but only a polynomial number of them sit in a constant range. Okay, a special case of this is a case that's sort of commonly considered is that where you have an actual gap. There's a constant gap between the lowest and the second lowest. But here we could think of the lowest as being degenerate, that there's more than one, for this eigen, I always get eigenvectors and eigenvalues confused. For this eigenvalue, there are several eigenvectors. And so we would be dealing with a case where there are up to polynomial and n eigenvectors. Okay, so for both of these cases, the big picture story is that we can describe these states efficiently. Remember, they live in an exponentially large space, so there's no a priori guarantee that you can. We can describe them efficiently in a way that we can work with them and compute local energies and various things from local operators. And in fact, we can find them. We can find these descriptions. So there's an efficient description, which is commonly known as an area law, and it comes in the form of, for those who know what a matrix product state is, it comes in the form that the bond dimension of the matrix product state is not quite polynomial. It's 2 to the poly log n for this situation. And that, in fact, you can find it in that same amount of time. And in this one, it gets a little bit better. It drops down to polynomial time. And there's a second case that sort of falls into this region, which is you could have a situation like this as long as you have a guarantee that just above it is some sort of constant gap where nothing appears. Okay, so these results come from, sort of in a context. This is not out of the blue. So let me sort of just back up a little bit and tell you sort of what's going on. So as Henry mentioned, in practice, people have been solving 1D problems for a long time very effectively by a sort of technique called DMRG. And they haven't been solving all of them, but they've been solving sort of a surprising number of them. Doesn't work all the time, but it works in practice very well. It's sort of what people use. So that's sort of there on the sort of plus side. And on the minus side, minus if you're sort of excited to, if you're physically oriented, I suppose. On the minus side is the fact that, in fact, this is a hard problem in general. Okay? So there are examples where the gap is 1 over poly. Okay? So there's a one state down here that's the ground state. The next states above are a gap 1 over poly, where it's provably hard to do this. Now, that you might say this seems like maybe it's in contradiction to what I'm saying, but these examples have an exponentially large amount of eigenvalues, eigenvectors in this sort of region right up in here. Okay. And then Matt did this great work of showing that for the first sort of provable case that that the ground state, if you're in this situation where there's a single ground state and then a gap, that there's an efficient description in the form of a matrix product state. So that in fact this notion that you might be able to work with it and that there might be something there that is workable and that you can describe without sort of overcoming this exponentiality existed. And then Umesh and Thomas and I managed to show that you could do that. You could actually find this state in this case where there is a single ground state. And then this was improved upon modestly to improve to the case where instead of a single ground state, you could have a log n amount of grounds in the degeneracy of the ground state. But going further than that, using these ideas, there was a significant obstacle. There was a significant obstacle. And without sort of going into the details, the biggest portion of that obstacle is there was no area law guarantee. So in each of these proofs, it relied on the fact that we knew beforehand that there should be an efficient description. Okay? And once you bump either the ground space up above log n, or you start talking about some of the scenarios we're talking about here, we no longer have those proofs. The proof techniques for those break down, and we have nothing to replace it with, so we can't rely on that, and so the algorithms just don't work. Okay, so that's the setting for a description of the algorithm. So here we are, and so now I'm going to go sort of move to the description of the algorithm. And I'm going to set the algorithm in a particular context, which wasn't the context that we were sort of originally doing, but in hindsight is the context that I think is valuable to think about it. And that's in the form of something called the renormalization group, which is a sort of physics perspective, which I'm going to describe very, very loosely. But it's a perspective that has been very useful in theoretical physics. And there's some speculation that it's also what's going on in deep learning for some of these deep nets. Why the deep nets are perhaps this effective. And so here's the cartoon version of the renormalization group, which is your, ignore that, or that somehow appeared too soon, but it doesn't matter. Here's the picture. So you have this exponentially large space, but we're going to sort of break it up into little chunks. Right? We're going to look at the little chunk, and what we're going to do is say, well, we don't really need all of the chunk. We're going to just take a little piece of that chunk out. Okay? So we're going to sort of single out little relevant bits somehow, right, at this scale. And then we're going to pass that information on to the next scale. So we're going to only consider these little bits, and then we're going to sort of think about the next scale and just this little bits. And we're going to now repeat, right? So we're going to extract a little bit out of that, and we're going to pass that on, and we're going to extract a little bit of that. And in doing so, we're overcoming this exponentiality, right? And from the sort of, I don't know, from the deep learning point of view, maybe we're feature extracting. So we kind of, after having come up with this algorithm in hindsight, we sort of think that really what we can sort of view what we're doing, which is rigorous, as some sort of rigorous version of RG. And that there's maybe some useful things to think about related to that. Okay, so how do we actually do the algorithm? All right, so let me remind you of the goal in the end, right? The goal in the end is to try to find this subspace of low energy states, right? It's a polynomial sized subspace of low energy states, but it sits in this very large exponentially sized system, right? So how are we going to find this thing, right? Because we can't sort of just dive right in where it's like, diving straight into the ocean where we're trying to find some seashell, right? I mean, we're sort of, there's no hope, right? So what we have to do is somehow start locally, right? And then sort of build up making partial progress. But when you start to think about that, you have the question of what does partial progress mean? Okay? So it's not so easy. A state is over a whole system. And so if we're thinking about, we have something on some small piece, and we want to think of it as partial progress, right? What does that really mean? We're going to try to get partial progress towards some subspace of the whole thing. And so what we're going to say what it means is the notion of a viable set. And a viable set says that if we use, on this piece, if we just use our little subset, and we tensor a product with everything on the remaining part, that the resulting big space that we get, right, is going to be close to this space that we're looking for. Or actually said it'll be bigger than the space that we're looking for, but this space that we're looking for will be near it. So this is this notion of a viable set. So what we're handling is small. Once we tensor product with something else, it becomes big, but it has a guarantee that it's close to what we want. Okay, so that's our notion of a viable set. So now what can we do with such a thing? So the first thing to notice is that if I just want a viable set on a small number of things, I can just take everything there. Right? So if I'm only dealing with a small number of particles, the exponential dimension doesn't kick in yet, so I can just take everything, and I have a guarantee that if I took everything, I would be close. So I can start, right? So now I'm sort of thinking, okay, if I can start, can I piece these things together? And so what happens for piecing these things together? So we're going to do this in a merge process. So we're going to start with thinking that this little blue thing says, I've got a viable set. I've got a piece that if I tensored it with everything else, would be good, right? So how do I put two of these together? Suppose I have two of these pieces on different bits. I want to sort of merge them together. So the first step you probably would think of, which is to tensor product them together. Okay? So something happens when you tensor product them together. You definitely get a viable set, but red is the indication that it gets worse. Okay? So the closeness gets a little bit worse. The dimension gets quadratically worse. And so you're not going to be able to continue to do this without fixing something, right? As you sort of do this more and more, you're going to end up with a very large space that's not very close to what you want, and so you could have done that from the get-go. So we're going to fix these two parameters by doing a two-step process. Okay? The first process is to just project onto a random subspace. Right? So what does that do? That fixes the dimension problem. Right? So you sort of take a random smaller subspace. That fixes the dimension problem, but obviously it does not fix the closeness problem. In fact, it makes it a lot worse. Right? So before you might have been modestly close, right? Now you've just taken some fraction of the space, you're not going to be that close at all. But by using randomness, you're going to be sort of average far away. So you're sort of the cut down in closeness is going to be some sort of average closeness. And so now we have to improve the closeness, and to do that, there's been in existence already a notion of a approximate AGSP, which is an operator and an approximate ground state projection, which has the effect of moving you closer, taking any state and moving it closer to the ground space by sort of clearing off some of the stuff that's farther away. And if you work hard, you can construct such a thing so that the amount of improvement in closeness is better than average. And if it's better than average, right, whereas the dimension that it builds up is average, then this is a positive trade-off, because the random projection has cut down by average. You're improving by better than average. So you can set it up so that you project and improve so that by the time you're done, though you've added dimension, you're still under the threshold of being a good dimension, and your closeness is back to being good. Okay? So this two-step process has sort of taken two viable sets and produced a third one on twice the space that's viable. So it's small dimension. It's guaranteed that if we tensor product with everything else, it's close. So what do we do now that we have this little unit? Well, right, we sort of stick it into a tree-like structure, right? So we combine and recombine and recombine. Right? And by the time we're done, what do we have? We have a viable set for the whole thing. Right? It's small dimension. It's guaranteed to be close to what we're looking for. Right? And so this is our new playground. Small dimension, guaranteed to be close to where we're looking for. Now we're doing linear algebra in this not exponentially large space, but polynomial size space. And we're okay, provided one thing happened. Okay? Provided that as I built up these viable sets, they all stayed in a way that was efficient to work with. Right? It's not enough just to produce these vectors. We have to make sure, again, these vectors are sitting in this exponentially large space. We've got to make sure that as we go along, they don't get too complicated. Okay? And the way we do that is we have to take a particular AGSP, we call this, I said it was smooth, but what it is it's an operator that has the property that we talked about, which was that it does better than average at certain places in terms of improvements in terms of bond dimension. But outside, it also has to not be terrible. And by not be terrible, it has to, from a matrix products point of view, state point of view, it has to be polynomial in n dimension, in bond dimension. Okay. And to do this, to construct this, it requires a notion of a soft truncation that comes from this work and modified to the original constructions of the AGSP. Okay, so just go back and sort of review quickly, right? So the algorithm consists of three steps, right? You start small. You do this merge process to go next steps up, building up this viable set. By the time you're done, you're in a playground where you're close, you're polynomial, you have an efficient description so you can work with, you can basically do linear algebra there. And so now you're solving a linear algebra problem. You can restrict your Hamiltonian to that space, and you can do it in any number of ways perfectly fine. And so you might ask, well, what, and it's reasonable to sort of say, I want to sort of point out what's new here. So there was, I mentioned at the beginning that the algorithms that existed before had a barrier, which was, there are two actual barriers. The first barrier is that there's no area law guarantee. Okay? So there's no guarantee that everything has a nice description, which was counted on. And the second is that when you start to have more than one state that you're going for, you run into trouble when you're trying to merge viable sets, because you don't know whether the viable set for the one and the viable set for the other was talking about the same place that you were shooting for, so you don't have these guarantees anymore. So those were the barriers that were set up before. So the notion of a viable set for subspaces rather than for a single element conquered this second of working towards the same solution, because you now go and attack all the solutions simultaneously. So by the time you're done, you're getting everything at once rather than picking off one at a time. And the merge process, right? The randomness replaced what used to be done with convex optimization. And the convex optimization, the only reason it worked was because there was a guarantee that there was an area law. There was guarantee that there was a solution there, right? So randomness we didn't know there was a solution there before we did the algorithm. When the algorithm provably works, that gets you the area law. So the randomness sort of overcomes the convex optimization point that required the area law. And the smooth AGSP allows for, which we didn't use in the previous one, but that was compensated for because we knew there was an area law, we could trim things down as we went along. So we knew there was an efficient description, so when things got too long, we could just trim them, right? And now with the smooth AGSP, we don't have to trim them, okay? Which is good, because we wouldn't be allowed to trim them because we had no guarantee that trimming them was leaving things in a decent place. And the tree-like structure is also essential for that. The previous algorithm worked linearly, adding one thing at a time. The tree-like structure gets things faster, which is important because otherwise you wouldn't, essentially you would run into the same trimming problem again. You'd be wanting to trim, but you wouldn't know that you could. Okay, so that's about it. So I guess I'll just sort of close with sort of saying, this RG there's something compelling here about algorithms and thinking about RG, where we sort of say, look, it's an idea that's really proved very fruitful in physics. Here's an example where you can kind of see a rigorous algorithm where you can see something of that going on. And I think there's something really there to sort of think about and ponder in terms of extrapolating what is actually going on and whether one can use it for other problems where we're trying to sort of extract things from a large set.
Any questions?
So is this algorithm practical? Have you implemented it or compared it to DNA?
I have not. What is? Do we know what? We know anything more than that fact?
We know as of a couple of months ago, we had some promising results, but we don't know what happens. So there's some work in progress.
I have a quick question. So you said there's some possible relation between renormalization and deep learning. Is there a way you can see, like, what are the analog of feature extraction in this algorithm? Like, what are the features that are being extracted?
I think it's sort of some analog of energy, right? So you're sort of locally picking out something, some sort of low energy, but there's some adjusting that goes on, right? Because you don't want to just pick out the lowest energy stuff locally because you might be creating problems for yourself later on. But there's some sort of adjusting that happens that sort of makes this all work. Umesh, do you have any other thoughts to? What's sort of the best that we can sort of say?
Let's thank Zeph again.